what I would like to do today is we'll talk about lime soda softening. And we have a situation here where you're given a composition of the water. So this is likely to be a groundwater, although in Michigan, we do have surface waters that actually do have significantly high hardness levels. And you're treating the water to achieve a final magnesium concentration of 40 milligrams per liter. So typically that we use that as a criteria, and that's because while both calcium and magnesium are the major contributors to hardness, magnesium is more costly to remove. It produces more sludge, and at concentrations greater than 40 milligrams per liter, the magnesium tends to precipitate out and coat the surfaces of heating elements. So this would be heating elements, for instance, on a water heater. This could be heating elements on a dishwasher. And that coating of the magnesium precipitate reduces the efficiency of the heating element. It means it costs more in electricity, costs more in gas if you're using natural gas. Hardness is equal to the sum of the concentrations of the polyvalent cations. Okay, so think about that as you're looking at determining the hardness for the first exercise. The other thing to think about is alkalinity. And alkalinity in fresh waters is equal to the concentration of bicarbonate
plus 2 times the concentration of carbonate
plus the concentration of OH minus minus H plus. Okay. Notice here that there is a 2 before the carbonate concentration. And the carbonate concentration here is in molar units or millimolar units, millimoles per liter. So that 2 comes from the fact that there are 2 equivalents or 2 milliequivalents per mole or per millimole. So that's equivalent to 2 milliequivalents per millimole for carbonate. Why? Because carbonate can accept 2 protons to form carbonic acid. For bicarbonate, N is equal to 1, exactly, because it can accept 1 proton to form carbonic acid. It can also donate 1 proton. Okay, so units are, in this case, millimoles or molar units, and we have a multiplier implicit throughout this equation. Now, for this situation, you're told that the pH is 7.2, which means that the bicarbonate concentration is approximately equal to the alkalinity. So why is this the case? 1, your pH is such, we're close to neutrality, so the concentration of H plus is approximately equal to the concentration of OH minus. So these 2 terms cancel. We can write what is referred to as a PC-pH diagram. And if you've taken 481, you've drawn these. If you're in 481, you're probably drawing these about now. So this is a description that P before C is just the negative log of C, just the same way that pH is the negative log of pH plus. So we can plot this as concentration of carbonic acid, and that will be relatively constant until it reaches the first pKa, which is about 6.3. At that point, its concentration decreases with a slope of 1, and now bicarbonate predominates. And bicarbonate will continue to predominate until pH reaches pKa2, which is about 10.3, and here carbonate predominates. And this also decreases with a pH of 1. These tend to cross around a pH of 8.3. So if we're in this pH range from about 6 to 8, then the concentration of carbonate is small compared to the concentration of bicarbonate. And this term is approximately equal to 0. So we can say that alkalinity is approximately equal to bicarbonate. So that's an important concept to understand. Total hardness is equal to the sum of the polyvalent cations. Sodium is monovalent, so it does not contribute to hardness. So the hardness is 127 plus 60, or 187. The carbonate hardness is limited by the amount of bicarbonate. So there's 157 milligrams per liter is calcium carbonate. So because alkalinity is less than the total hardness, then the carbonate hardness is equal to the alkalinity. The non-carbonate hardness is the difference. So that's equal to 30. Okay. What I didn't draw before, and let's draw it now, is what's referred to as a bar graph. So typically what we do is we put the anions on the top and the cations on the lower bar. The alkalinity is 157. So this is our bicarbonate concentration. The calcium concentration is 127. And the magnesium is 60. And that is then 187. Okay. Sodium, we could put sodium on the bar here. Okay. And that would add the sodium. This would be sodium. Typically then we would add chloride, sulfate, nitrate here. So this would be chloride, typically sulfate, nitrate. And typically in that order, because that's in order of prevalence. So now we can think about this in terms of the carbonate hardness due to calcium. And I'm going to switch. So the carbonate hardness due to calcium is this portion right here. All of our calcium, we can assume, is associated with bicarbonate. Magnesium that's associated, the magnesium that's associated with carbonate is the portion that I've shown in blue. So that then is that portion. Okay, so we've got this here is 30. So that means, so this is equal to 30 milligrams per liter as calcium carbonate. Okay, so that's the carbonate hardness due to magnesium. The non-carbonate hardness due to calcium is equal to what? 0. And then the non-carbonate hardness due to magnesium is what's remaining. So do that in green, and that is 30 milligrams per liter as calcium carbonate. Okay, so that bar graph is helpful in order to think through how these ions are distributed, and therefore helpful in the next step in terms of determining what reactions will actually occur. So the next step is to think about, do we need to reduce the concentration of magnesium? So our magnesium concentration is 60. Do we need to reduce it? Typically, if the magnesium concentration is greater than 40 milligrams per liter as calcium carbonate, it tends to precipitate out, coat the heating elements, reduce the efficiency of heating, which costs us in electricity and natural gas. So for that reason, it's used as a design parameter, and we want to reduce it to about 40 milligrams per liter. Okay, so the answer is
Yes.
in terms of the actual process limitation. So the 40 milligrams per liter magnesium is typically what we then design what we call a split system for, in order to reduce the problems dealing with precipitation on heating elements. However, we have process limitations. Okay? We can't achieve 0% hardness, or sorry, 0 concentrations of hardness. We can't achieve 100% removal of our hardness in a chemical softening system because of a number of process limitations. And those include, one, the solubility. So we're precipitating out calcium as calcium carbonate. And we can write an equilibrium expression for that. There will be some calcium remaining at equilibrium. We can write an equilibrium expression for magnesium hydroxide. We precipitate the magnesium as magnesium hydroxide because it's less soluble than magnesium carbonate. And we also have a solubility product for that. So even at equilibrium, we will have some magnesium left in solution. The other issue is that the reactions may not be complete. Acid-base reactions essentially are instantaneous. Precipitation reactions take time, and there may not be sufficient time to even reach equilibrium. There may be non-ideal mixing, short-circuiting in the reactor. So as a result, typically the minimum calcium hardness that we can achieve is about 30 milligrams per liter, and the minimum magnesium hardness is about 10. So even where we soften to the stoichiometric amounts, you will still see calcium and magnesium in the effluent. Okay. So in terms of the split ratio, that is determined from magnesium concentration, that the final magnesium concentration, which typically we design to be 40 milligrams per liter, minus the magnesium concentration from the first stage, divided by the raw magnesium concentration minus the magnesium concentration from the first stage. And this is equal to our bypass ratio. So what I would like you to do in the next breakout room is draw a schematic showing split flow treatment. And if you've done that and you still have some time, take a look at the next set of reactions and see if you can determine the stoichiometry. Okay, we'll go through that, but if you have some time, you can do that. So I'm going to form the breakout rooms again. I'm only going to give you about 5 minutes so that we have more time to discuss, okay, at the end. So what I want you to do is in your breakout rooms, draw a schematic showing typical split flow treatment. What do you think that would look like?
So let's draw a schematic showing the typical split flow treatment.
We have raw water. So if we have groundwater, the screens are actually in the well if there is screening. It's not always the case. Okay. We would typically have a rapid mix basin where we're adding our chemicals, followed by a reaction basin, which essentially is a flocculation basin, except we're not flocculating, so therefore it's referred to as a reaction basin, even though the design is identical. Followed by sedimentation, and we have the split flow here. So this is our split bypass, and this here is 40 minus 10 over the raw water was 60 minus 10. So that is 0.6. This is 0.6 here. So we're going to treat 1 minus x is equal to 0.4. So we'll treat 40% of the flow. Now, pH of this water is typically between about 10.3 to about 11.3. We can't distribute water at that pH. It's highly corrosive. It would feel kind of really slimy. So we have to reduce the pH. We can either reduce the pH by mixing, and that works in some cases depending on the alkalinity, depends on the ratio of bypass, or we use what is referred to as recarbonation. So here we're adding CO2. So we add CO2 gas that reacts with water to produce carbonic acid, which results in a pH reduction. And if you measure the pH of East Lansing water, typically it's around 8.5 to 9. So it's actually quite a bit higher than you might have thought it would be. Now we may have sedimentation. We can also have a second stage where we actually add more lime or more soda ash, depending on the process. Any questions about this? So the next thing I want you to think about are the stoichiometric amounts of soda ash and lime that are needed, and we can also calculate the amount of sludge.
Sorry, where did the 40 come from for the magnesium?
The 40 here?
Yes.
Typically, we're designing it for 40 milligrams per liter. And that comes from, did I write it? Maybe. That comes from the fact that at concentrations greater than 40 milligrams per liter, we tend to have problems with the magnesium precipitating out on heating elements. Okay. We could reduce it more, but it just costs us more. Okay. And you'll see that in just a little bit when we go through the stoichiometry. So looking at the stoichiometry, okay, we have 19 milligrams per liter as calcium carbonate. Because CO2 reacts with water to produce carbonic acid, N is equal to 2, which is the same N is equal to 2 for calcium carbonate. So we can divide this by the molecular weight of calcium carbonate. So this is molecular weight of calcium carbonate. And that is equal to 0.19 millimoles per liter. Typically, we add lime as calcium oxide. This is quicklime. It is more stable than hydrated lime, but when we add it to water, it produces hydrated lime. Problem is that hydrated lime actually absorbs CO2. So this is what we would purchase. This is also an exothermic reaction. So it gives off heat. So typically this is done in a controlled environment, significant ventilation to remove that heat, significant protection to protect someone from getting burned because of the heat that's released. So we have, or what we will need is 0.19 millimoles per liter of calcium hydroxide, or lime, and we will produce 0.19 millimoles per liter of sludge. Notice we're spending money on lime and we are producing sludge, but we're achieving no hardness removal. So it's costing us in money, both capital costs, and it's costing us an operating cost, both in chemical use and sludge production. Now we calculated the carbonate hardness due to calcium. We said that that was 127 milligrams per liter as calcium carbonate. Again, divide by 100 milligrams per millimole, and that is equal to 1.27 millimoles per liter. So we have 1.27 millimolar. We need 1.27 millimolar. And notice we actually, for every 1 mole of calcium we remove in hardness, we produce 2 moles of calcium carbonate sludge. So here, this is 2.54. So what you're going to do is basically bookkeeping. Okay. The carbonate hardness due to magnesium is equal to 30. So again, it's 30 milligrams per liter. It's calcium carbonate. Divide by 100 milligrams per millimole. And that is 0.3. So we have 0.3. Okay. In this case, again, we have a stoichiometric ratio of 2 to 1. So we need 0.6 millimolar. And notice here we have produced 0.3 millimolar of magnesium hydroxide sludge plus 2 times that 0.6 millimolar of calcium carbonate sludge. Questions? If it's relatively, it's basically bookkeeping, okay? Non-carbonate hardness due to calcium, we said that this was 0. And we have 30 milligrams per liter as calcium carbonate divided by 100. So that's 0.3. So we have 0.3, 0.3. And now we need soda ash. Soda ash is more costly than lime. we again produce 0.3 millimoles of magnesium hydroxide and 0.3 millimoles per liter of calcium carbonate. So in terms of the amount of calcium oxide that we need, now we just add up. We have 0.19 plus 1.27 plus 0.6 plus 0.3, and that is equal to 2.36 millimoles per liter. Okay. For soda ash, we only need 0.3. Okay. We can do the same thing for the sludge. So for calcium carbonate, we'll do the same. Now we've got 0.19 plus 2.54 plus 0.6 plus 0.3, and that is equal to 3.63 millimolar. And then for magnesium hydroxide, that is equal to 0.3 plus 0.3 or 0.6. Okay. The last step in this type of a calculation is the determination of the mass that we're producing. So and we have 0.05 meters cubed per second. We're treating 40% of the flow. I'm going to multiply that by 86,000 seconds per day times the amount of calcium carbonate that we produce times the molar mass times a conversion from liters to meters cubed times a conversion from milligrams to kilograms, and that is equal to 627 kilograms per day. Okay, we're a minute over, so I'm not going to go through the calculation, but for magnesium hydroxide, we would use the molar mass of magnesium hydroxide, and this would be 60 kilograms per day. So these are the dry, remember, these are dry weights. Typically, it's going to be your sludge is, in this case, typically with gravity settling, it's going to be somewhere around 10 to 20% solid, so it still has a significant amount of water. So you can imagine, okay, get an idea of the amount of sludge that's produced.